Hello guys, welcome back. Now it's been a while or so. Now these are the questions requested by students. In this case, by one of my viewer or one of the students called Janice. I have to apologize that it's been a long while before I'm able to produce a video for her. All right, so hopefully it's not too late. Now this is the video for mechanics. Okay, I think it's one of the June 14. Yeah, it's a June 14 paper. Paper 43. This is question 7 here. Right. Now let's go through this. So here you have we are given a slope, and then it says that this slope is a smooth inclined plane or slope in this case of length 160 centimeter is fixed with one end at a height of 40 centimeter above the other end, which is on a horizontal ground. Particles P and Q of masses 0.76 kg and 0.49 kg respectively are attached to the ends of a light inextensible string which passes over a small smooth pulley, and Q hangs vertically below the pulley at a height of 30 centimeter above the ground, as depicted in the diagram. P is released from rest. It starts to move up the plane and does not reach the pulley. Now, the first question is to find the acceleration of the particles and the tension in the string before Q reaches the ground. Okay, right. Let's take a look at all the informations given to us first before we answer any mechanics questions. That will be the usual methods to solve a mechanics problem. This is more like a classical mechanics problem. Right. Now, first of all, we're going to the four most important things to do in mechanics question is to label um, all the forces acting on all the objects in the system itself. And then, of course, you must be wondering why they give us the dimension for the slope. Right. The main reason is because we can sort of know the steepness of the slope itself. So here I'm going to write down the steepness itself can be represented using, in this case, best represent using sine. Sine theta is equal to, we know that the height is 40 here, so therefore is a quarter. All right. And then, of course, from here you can also produce some other ratio. Take for instance, if you need them sometime. Take for instance, you can produce cosine theta in this case, whereby the cosine theta will be sort of like in this case will be cert 15. Okay, so cert 15 over 4. Right? You can do this by, okay, now let me show it to you first before we actually get that. Now, because sine theta is 1/4, so you can actually draw out a right angled triangle, for instance. So I'm going to draw out a right angled triangle here, and then this is theta. The ratio is 1 to 4 here, 1 to 4. All right, and then therefore you can find this missing length, which is 15 in this case, cert 15 to be precise. Right, now that's the reason why you have your cosine theta is equal to cert 15 over 4. Or indirectly, you can also access to your tangent if you need them. Right, so I hope that is clear. That is the first geometrical informations that you can get from the diagram. So always try your best to obtain any geometrical informations you can from the diagram itself. And then next, we're going to label the forces, as I mentioned. First of all, we do have the weight itself. We have P as a 0.76. So here I'm using G as 10 Newton per kg. right, for our analysis here. Therefore, the weight for P would be 7.6 Newton here. And then at the same time, of course, we do have the normal force uh, in this case, but anyway, we don't actually need to use them. Okay, and then next, you have to label this angle here. This angle is actually the theta also. This angle is theta, all right? And then you have your tension due to the string. And then, of course, the same thing happened here. There will be a tension acting on the pulley in this case. And then at the same time, we have the tension acting on the um, particle Q in this case. And then lastly, the weight of Q, which is 0, oh, sorry, no, it's not 0.4, it's more like 4.9 in this case. Okay, and then once you've done this, do check and have a glance. Have we actually fully utilized all the informations? I think at this point, yes, we have fully utilized. Now we are ready to answer the first question. Now, to do that, we will label the acceleration as A. Because the system is attached and then the string is inaccessible, so we can assume that the P and Q would accelerate at the same time and then would have the same acceleration, right? So next, we're going to consider all the forces acting on one particular object. You can actually consider the entire object as one object, but it's always easier to apply divide and conquer strategy. So here is better we're going to consider forces acting on P first. Take for instance. And then now do bear in mind that the object is accelerating. Therefore, Newton's second law is applicable in this case. All right. So Newton's second law is F equal to ma. Net force, we are looking at the direction is moving up the slope. So therefore, our resultant force or net force that is acting on the particle P would be, we can see that there's one force acting upward T, and then there is another force due to gravity that is acting downward. But you have to resolve the downward component here. Therefore, we will say that the resultant force acting on particle P as T minus 7.6 sine theta is equal to the mass for the particle P, in this case is 0.76 acceleration. And then we do know the sine theta as a quarter here. So you might want to simplify before we proceed further. And then we can take a quarter of this. All right, so that will be like 1.9. After you simplify, it should be 1.9 there. All right. Okay, and then that will give us the first equation. All right. Okay, so I hope that is clear in this for this part here. Now to resolve the component, I hope that is clear. I can roughly draw that diagram down one more time, just in case some of you forgot how to resolve the forces. This is particle P here, and then there is a weight component 7.6, and then we have the dotted line here. We are trying the slope is in this direction, so we are trying to resolve the forces along the slope itself, which is here. This is 90 degree. Now if you apply your SOHCAHTOA, if you assume that the length for this line hypotenuse is 7.6, right, 7.6, then we will have that, let me label that correctly. So this is 7.6 here. And now if you want the component of the weight that is parallel to the slope, then that will be, if you apply your SOHCAHTOA, it will be 7.6 sine theta, whereby the vertical component would be 7.6 cosine theta. Now, just in case you're wondering why do we need the vertical component there? Now, if in the questions they require the normal force acting on particle P, then yes, you can use this component here to state that to state this. Okay, now this is just extra informations. You don't really need that for this question. I'm just showing it to you. If you consider the forces acting on P, that is perpendicular to the slope itself. By using Newton's second law again, we have R minus 7.6 cosine theta is equal to 0 because the particle does not accelerate in the perpendicular directions to the slope itself. Now from there, you would be able to find out the reactions force here. Okay, now I'm going to pause here for a while for you to organize your thought. Yeah, digest the informations. Yep, think about this. Hopefully that is helpful. All right. Okay. So once we're done this, we don't need this anymore. I'm going to erase it off here. Now, next, after we're done with the considering the forces acting on particle P, we can perform the same method by considering forces acting on Q instead, this part. And then if you look at the forces that is acting on Q, there are only two of them. And then because the particle Q is accelerating downward here. Now, bear in mind, Q is not under free fall acceleration. So we don't actually use 9.81 or 10 meter per second square because the Q is attached to a string, so it does not fall freely under gravity. It fall due to the tensions and the weight of P also, right? So by considering the forces acting on Q, we will have 4.9 minus of T that will produce the downward acceleration, which is 0.49 A. As I mentioned before, it's the same acceleration, I would say same magnitude in terms of the acceleration. Now that will give us the second equation. All right. Now in order to solve this easily, I might as well write this one down side by side, so it's easier for you to digest the simultaneous equation. Okay, this one is our second equation. Now, solving this simultaneous equation is a piece of cheesecake, I think, for most of you. All you need to do is just, we are interested in the acceleration, so the step taken would be, the best method would be elimination. So we want to eliminate the t by adding up these two simultaneous equations. We will get, this is 1.25a, and then that will give us a 3, and then that's it. All right, so from here you can use your calculator on that. All right, so let me see, 612, so the acceleration should be 0.12, right? So just let me check with my calculator, double check in case I make mistake on this. All right, so I think it's 0.12 in this case. Oh, okay. I'm wrong in this case, right? After I check my calculator, it's supposed to be 2.4 meter per second square, right? Now you guys can also check with your own calculator. Now verify that that acceleration is 2.4 meter per second square. And then there you go. That's the first part, acceleration. Once we have obtained the accelerations, now getting the tensions would be quite direct. Let's assume that I'm using the second equations to gain access to the information for tension. Then by rearranging this, I will get 4.9 minus of 0.49 acceleration, so 2.4 here. And then doing a bit of calculation here, just let me check what do I have here. Minus of 0.49 by 2.4. So therefore, the tensions will be 3.724 Newton. Of course, in the exam, they do allow you to leave it as like minimum 3 centimeter figures or more. All right. So I'm going to pause here. Um, you can look through number one and then cross-check with your own work also. All right. Now, we're going to move on to the second one um, shortly. All right. So let's look at the second one now. Okay. We have obtained the accelerations of the system as 2.4 and then the tension as 3.724 from question 11 from question part 1. All right. Now next we are going to look at how do we find the speed with which Q reaches the ground. Okay. Now initially we know that Q started off from U equal to 0 meter per second just now, right? So from here we can actually make use of the Suvet equations because we know the distance from the start of Q until it reaches the ground as 30 centimeter. Right? We can use that with the informations of acceleration. We're going to choose the right Suvet equations to find the speed of Q just before it reaches the ground. Now, in this case, I think that without the informations of time, the best Suvet equations to use will be v square equal to u square plus 2as here. And then v is the speed um, for the particle q just before it touched down. And then u, we know that initially it was 0 meter per second. All right, so we're going to substitute that. And then acceleration. Acceleration from here we have 2.4, and then we know the distance that you need to travel from the start until it reaches the ground as 30 centimeter. But do bear in mind, in this case, if you want your answer to be meter per second, you might want to convert the unit to from centimeter to meter, 0.3 here. And then from here we are good to go. All right, so just let me quickly check the answer that we have. We have let me see here, we have like 4.8 here. All right, so we got a very nice number after you square root that. We got one, I think is v square is 1.44, and then the v is 1.2 meter per second. And then there you have it. That's the speed of Q when it reaches the ground. And then do remember that because they are attached to the inextensible string, so when Q reaches the ground with a speed of 1.2, P would also achieve the same speed when P has moved 30 centimeter up the slope. Now that is the understanding at this point, right? So I'm going to pause here for the second question. You can organize your thought and cross-check your answer there. Right? I'm going to move on to the third one shortly. Right, now next let's look at the third sections of this. We need to find out the total distance traveled by P before it comes to instantaneous rest. Now I have redraw the diagram for the object on the slope. At this point, once the P has reached the ground, once the Q has reached the ground, the P would have moved 0.3 meter up the slope. And then once that happened, when Q reaches the ground, then the string would be slack, meaning that there's no longer any tension acting on the string. All right, so you can still apply the same Newton second law. All right, now I'm going to apply the same Newton second law on this, which is F resultant force is equal to ma in this case, whereby the m in this case is 0.6, and then the acceleration is the one that we want to find out what is the acceleration of this particle P after the tensions become zero. When the tension becomes zero, if you use the previous equations that we have set up for Newton's second law, which is T minus 7.6 sine theta is equal to 0.76a. Now we can make use of the same equation, but we're going to let the T equal to 0 because when Q reaches the ground, the tension should be 0. So when that happens, we put in 7.6 and then by a quarter, if you still remember, I forgot to rewrite this one more time. The sine theta is equal to a quarter, and then we have 0.76a here. We have found that when the string is slack, therefore the accelerations will become deceleration, I would say, right? So let us try this one out. The decelerations will be equal to, all right, so this one will be, let me see here what we have. That will be like 100 here, 1000. So it should be 76, should be 16. Did I get it right? 19, should be 19, right? Should be a 19 or 1.9. Let me check. Let me check one more time in case I make mistake on this. I think it's 1.9. Yeah, correct. So hold on. Okay, and then multiply by 4 here. Did I get it right? Hold on. I make a wrong calculations here. This is a very simple task here. Hold on. Yeah, correct. So it's actually negative 2.5, sorry. So it's negative 2.5 meter per second square, the decelerations that is experienced by particle P in this case. All right. So I hope that is clear. And then you must be wondering, why do we need the decelerations? Because we are going to analyze the second motion of the particle P when the string is slack, right? And then when it is at an instantaneous rest, the velocity would be equal to 0 here. So we are very interested to find out how far the P would have moved before it stopped momentarily. And then we will get the distance that it moved from A to B here. All right. Now from here we can make use of SOHCAHTOA. SOHCAHTOA. We can make use of the kinematic equations, or SUVET in this case. We're going to choose the right SUVET equations again. So we're going to use V square equal to U square plus 2AS. And then we know that the final velocity must be equal to 0. The initial, yes, this is one informations that I have forgotten to find out, the initial velocity at this point A here, when the particle Q has reached the ground. What will be the speed of the particle P when it has moved from O to A here? I'm going to label this as U. We're going to find out U first. Okay, I think I'm going to locate U first. To find U, all we need to do is apply the SUVET equation, the same SUVET equations, V square equal to U square plus 2AS in this case, but we are looking at the motions from O to A. So here I'm going to write down OA. We only look at the motions from O to A when the string is still sort of taut in this case. Now that U that we are using is actually the V from our SUVET equation. All right, now from here, initial U here is a 0, and then the accelerations that we have already found out when the string is still taut is 2.4. So it's 2.4. Distance move is 0.3 here, and then from there we have already found out the answer in our previous question, as I mentioned before. This is just for checking purpose. You might want to check one more time what would be the speed, as I mentioned before, when the Q reaches the ground with a speed of 1.2 meter per second, the particle P would also achieve the same speed. So these calculations just verify our assumption just now. All right, so I hope that's clear. Now we are going to use this as 1.2, the u as 1.2 here. So this u become 1.2 at P. Okay, I'm going to label that 1.2 meter per second. Okay, we're going to use this and then apply the Suvet equations one more time, but this time we're going to analyze the journey from A to B. Using the same Suvet equations, the V becomes 0, and then the U is 1.2 square plus 2 accelerations for the journey from A to B is very different from the acceleration for the journey from O to A, because O to A is under tension, A to B is mostly gravity. Right now, therefore, we have to use the second accelerations that we have found here, which is negative 2.5. And then the distant move is the one that we are interested to find out how far it will be able to go up the slope before it stop momentarily. All right. So from here, once you rearrange that, you should be able to find out the answers to be. Let me check that in case I made mistake one more time. That will be like is it a 5? Yeah, correct. Divided by 5. So therefore, the distance move here is 0.288 from A to B. From A to B. All right. So I hope that is clear. Therefore, finally, they want us to find out the total distance traveled by P before it come to rest. Total distance traveled by P from O to A. So total distance traveled by P is equal to OA plus AB. And then OA we know that is 0.3, AB is 0.288, and then finally we can get the total distance as 0.588 meters there. All right, now I'm going to pause there for a while. I hope that that is clear to all of you. All right. Now, do drop some comment if you still have any questions on this, right? So I'm going to move on to the next requested question, right? So that's all for this question here. All right, welcome back. This question is also requested by Janice. I think she has requested a few questions that I did not have opportunities to complete the video for her. So here we go. I hope that it's not too late again, right? Since the exam is just around the corner there, right? So I hope this is helpful. Let us get through this here. We are looking at a pulley system, and then the way how the pulley system behave is also depicted by the graph at the side here. This graph basically shows us the motion of either one of the particles there, right? So let's read through. We have two particles P and Q have masses m kg and 1 minus m kg respectively. The particles are attached to the end of a light inextensible string again, which passes through over a smooth fixed pulley. P is held at rest with the string taut and both straight parts of the string vertical. P and Q are each at a height or h from the ground. P is released and Q moves upwards. Subsequently, Q hits the ground and comes to rest. Now, figure 2 shows the velocity time graph of particle P in this case, while Q is moving downwards or is at rest on the ground. So when Q is at rest on the ground, P is still moving. So therefore, this entire graph represent the motions of P when before the Q reaches the ground and after the Q has already reached the ground. All right. Now, first of all, we're going to label, as I mentioned before, we're going to label all the forces that is acting on the particle itself. So we have here, uh, is, I would say 10 m to be precise. You can just put in 10 m here. That is the weight of particle P. And then for Q, we have 10, 1 minus m Newton in this case. All right. So those are the two forces. And then don't forget, at the same time, we have the tension here. Okay. Now those are the tension um, exerted on the string itself. All right. Let's check through if we have any other informations there. All right. So generally, that's how it is. And then it is mentioned that once the pulley system is released from rest, Q start to move downward. So Q moves downward. Now, because Q moved downwards, right? We know that the mass of Q must be greater than mass of P. So for that, we can put aside a bit of a small analysis. We will say that, all right, now due to the conditions of the mass Q greater than P, we know that the mass of Q is much greater than P, and then we know the mass Q as 1 minus m, whereby mass P is just m. By rearranging this, we will find that the value m itself is less than 0.5. Now, this is just an extra algebra that will help us to check whether the answer that we got in some part of the sections down there is logical or not, based on these conditions given by the question itself, right? Okay, let's look at the first part. Find the value of h, which is the height of P and Q from the ground initially, right? So how are we going to make use of the graph here? Right? If you look at the graph itself, it actually takes 0.5 second for Q to actually reach the ground. Okay, when Q has reached the ground, P would have certain velocity. P would have certain velocity while the string is still taut. Or while the string is still taut, P would have certain velocity when Q reaches the ground there. Or we can say that the speed of the Q when it touches the ground is exactly the same as the speed of P when it reaches that, when it has moved h, when the particle P has moved h meter up from its original position. So when Q moved down h, P would have moved down h meter up. Now, this is depicted in the graph itself. It would have moved h meter up. And then when it moved h meter up, the speed of P at this point here is equal to 2 meter per second. That is what is shown here. You can see that it has sort of reached the maximum speed. And then once Q has reached the ground, the string becomes slack. So when the string becomes slack, the object P would fall, would still move up. Actually, it will still move up. It doesn't stop here. It will still moving up, but the force of gravity will be pulling it down. Therefore, that object will experience the gravitational deceleration in this case. All right, when the string is no longer taut, or when the Q has reached the ground itself. All right, so I'm going to show it to you how it look like at the side here. So what happens is that when the string become slack, that is when Q has already reaches the ground, right? At that point, just before it becomes slack, the velocity of P at this point is 2 meter per second. So P is here at this point. The velocity is 2 meter per second. Just before the string becomes slack, or when Q has reached the ground there. And then do remember, P has already moved h meter. I'm going to write down here. it has already moved h meter when Q has moved h meter down. All right, so that's how it will look like in this case, right? So that graph is very obvious. It takes 0.5 second for Q to actually travel down the distance of h, and then for the P to move up h meter also. All right. Now to find that distance itself, it will be bear in mind in the exam whenever you are given a velocity time graph, there are only two properties you should watch out for. The first one is a gradient of the graph itself, gradient of the velocity time graph. Secondly is the area under the graph. So area under the graph is the one that we are interested in because the area under the graph represents the distance traveled. So here we're going to make use of the area under the graph to find the h itself. Now, therefore, we can say that the h is basically the area under the graph from 0 to 0.5 second. That will be 2, 0.5. All right. So therefore, particle P has already moved 0.5 meter up, and then Q would have moved down by 0.5 meter, and then the value for h is 0.5 meter here. All right. So I hope that is clear for the first part. Okay. Okay, yeah, right. So now I'm going to move on to the second part. Right. Now for the second part, I'm going to clean this up a bit. So it's a bit messy here. We don't really need this. Okay, we just need the tension itself. Okay, so these are the forces that is acting on the pulley system. Now we need to find out the value for M and find also the tension in the string while Q is still moving before it actually touched down. All right. So before it actually touched down, that's the thing. Now, for this, we know that both of them would experience the same acceleration. P will be accelerating upward, whereby Q will be accelerating downward. And then one informations that we can extract from the graph itself is the accelerations of P and Q just before the Q touchdown. And then these informations can be obtained from the gradient of this graph here. Therefore, the accelerations of the particle is given by 2 over 0.5 here, which is 4 meter per second square. Right. Okay, I'm going to pause here for a while. You guys can use your calculator to check if you agree with this. Okay. Right now, that is the accelerations that we need. And then, as usual, we can set up the same Newton's second law for the second question here. By considering, I'm going to start off by consider forces acting on P. Forces acting on P, that will be T minus 10M must be equal to MA then. A we have already found out, so I'm going to write it down as M4, or you can rewrite as 10M equal to 4M here. We can label it as equations number 1, or in this case we don't have to waste time on that. We just need to solve this, and then the tension is basically just 14M. So the tension is 14M. I'm still going to label this as number 1 because we have not found out the value for M yet. Okay, now the second equations that we can obtain is by considering forces acting on Q instead. Right, so that will be 10 minus of tension is equal to 1 minus M A, which is a 4 here. And then now the same thing here, we are going to rearrange this. Okay, so if we rearrange this, we will be able to, okay, I can show that if we rearrange this, we can have You can simplify the 1 minus m if you want. If you don't want, you can substitute the 14m directly into number 2. So I'm going to say that substitute number 1 into 2, for instance. Okay, so from here you have 10, 1, 1 minus m minus 14m is equal to 4, 1 minus m here. Okay, and then with a bit of simplification, okay, so this is like 10 minus 10m minus 14m equal to 4 minus 4m here. Right. We would like to collect all the like terms on one side, of course. Right. So that will be like if I bring all the m over to this side here, I will have 20. So it will be 20m is equal to 6 here. So if I bring this 4 over, it will be 6, right? So therefore, the m that I got from here definitely going to be 0.3 kg. So if we check back, if we want to check back whether the mass that we have obtained is logically correct, then we will come back to the same conditions that we have set before this here to see whether the m does make sense. Yes, it does, because the mass has to be less than 0.5 kg, and then we did get a value of m which is less than 0.3 kg, right? So I'm going to hold that value for a while, and then we're going to make use of that value to find the tension. Of course, that should not be any problem. You just need to substitute the m back into here. Therefore, the tension itself is 14 by 0.3 there. So that will be like 4.2 Newton there. Okay, I'm going to pause there. I hope this is clear to all of you. You can check and then organize your thought. Think about that. Hopefully it is helpful in your study. Okay, all right. Okay, once you're done that, we are going to come back to question 3 shortly. All right, welcome back. Let's look at the last section here. Now, here I have already drew two conditions for the moment when the string is slack, or when the time when particle Q has reached the ground. That is the point when the string is slack. And then particle P will continue to move under the gravitational force until it reaches the maximum height. As shown by this diagram here, it will go up until you reach a maximum height. At maximum height, the final velocity must be equal to 0 here, and then it's going to return back to its condition, to its position here. Once it reaches here, the string will become taut again, because once it reaches here, this is exactly the same position when the string start to slack. So when you come back to this position, that is the time when the string will start to taut again. All right. So we want to find out how long does it take from that moment when when Q has reached the ground until it go up to the maximum height and come back to this position again, right? But anyway, the questions did mention that the total time from the instant P is released. From the instant P is released, the instant P is released from here, from O here. Take for instance, the time taken from O to P, right? We have already found, figured that out from the graph itself. So this is the time taken from O to P, which is 0.5 second anyway. Right? So I hope that's clear. Now all we need to do is to find out how long does it take to go up and come down to the same positions again. When I say come back to the same position, it means the final displacement is equal to 0 meter. And now that's the key thing that we're going to use here. So based on the Wright-Souvet equation, S equal to ut plus half at squared. Right. We know that the final displacement is 0 when we return to the same position again. our initial velocity when q has reached the ground is 2. So here we're going to rewrite that as 2t, and then once the string is slack, or when the q reaches the ground, the only force that is acting on the particle p is gravity. So therefore, it would be something like a particle that experiences a free fall acceleration. All right, so there's no longer um, forces found in the string itself. It's purely gravity. Right now, because particle p experience gravitational acceleration, therefore this would be half a is -10 here, t square is equal to 0. So by simplifying this, we have 2t minus a 5t square, and then of course you can factorize that quite easily. Hold on, made a mistake here, let me correct that. So that will be a 2 minus 5t here, and then that would actually give us a 0 or a 0.4 second. Of course, the 0 is the initial time. How long does it take to come back to the positions when the string would start to tau again? Is 0.4 second. Therefore, we can conclude that the total time required by these questions from the instant that P is released until the instant when the string becomes tau is given by the time taken from O to P plus the time taken for the second journey here, where the P move up under gravity and then come back to the same position again. Now that will give us 0.5 plus 0.4, that would be 0.9 second. Right? So I hope that is clear for this question. All right, now I'm going to proceed on to the next one shortly. All right, welcome back. This is the next questions also requested by Janice here. Right, let's look at this one here. We have a pulley system again. Particles A and B of mass 0.3 and 0.7 respectively attached to the ends of a light inextensible string. The string passes over a fixed smooth pulley. A is held at rest and B hangs freely, with both straight parts of the string vertical and both particles at a height of 0.52 meters above the floor. Right now, A is released and both particles start to move. All right, A is released and both particles start to move, and then guess what? For sure, B is going to move downward, A is going to move upward, and then the first questions require us to discover the tension in the string. At the same time, we can also find out its acceleration. Okay, all right, let's give it a try for the first part. We can, as usual, we can label the forces that is acting on the pulley system itself. We can label it as T, and then there's the weight acting downward. In this case, it will be 3 Newton, and then the same thing goes here. We have 7 Newton, and then we have the same tension here. We know that the accelerations is downward for B, acceleration is upward for A here. Okay, and then the distance is 0.52. Okay, now by applying the same procedure that we have done previously, we're going to consider the forces acting on that individual particles. Okay, so the first one we're going to consider forces. Okay, here I'm going to say consider forces acting on A and B. This time we're going to combine both of them. Now, by using Newton's second law, we are using Newton's second law. Here, I just write down this formula as a reminder. Okay, we're going to apply the same Newton's second law for the motions of A and B. Okay, so for A, it will be T minus 3 is equal to 0.3A. That's our first equation. Then for B itself, it will be 7 minus the tension. Okay, 7, I better put a cross here just to signify that 7 is equal to 0.7 A. Okay, solving this simultaneously as usual, we're going to add up both of the equation. We will get A equal to a 4 meter per second square directly. Right, and then once we have done that, we can substitute this into either one of these. Take for instance, I'm going to use equations number 1 then. So tensions minus 3 is equal to 0.3 by 4, which is 1.2. Therefore, tension is equal to 4.2 Newton. And then there you have it. We have done the first part. Right, I'm going to pause here for a while. You can organize your thought and then take out your calculator and give it a shot whether it make the same sense as what I have wrote down here. All right, so I'm going to pause here. We're going to proceed on to the second one shortly. All right, let's take a look at the second question here. When both particles are moving with speed 1.6, the string breaks. This can be shown by this diagram that I have drawn just now. You can see that when the particle A move up to a certain distance from where it started from, its speed is 1.6. That is the moment when when the string start to break. And then at that point, when it start to break, the speed of B is also about 1.6 meter per second. Right? And then here I'm labeling the distance that particle A move from its initial positions to the positions when the string start to break as x. And then the total distance from the moment when the string start to break until the distance from that moment when the string start to break to the ground, right, is given as x plus 0.52 meters. This is exactly the same distance at the positions when the strings start to break, and then we will take this distance at this moment to the ground as x plus 0.52 meters here. All right, so those are the informations that we have. I think at this point we are quite interested to find out how far it has moved from its initial position just before the string breaks. Okay, we're going to find out x first by using the Suvet equation. All right, so we're going to find x by using the Suvet equation, and then we know that initial speed here is 0 meter per second. The Suvet equations that we can use will be v square equal to u square plus 2as, and then the v itself will be this part here, 1.6 square. The u is 0. Acceleration, we make assumptions just before the string break. Its acceleration is the accelerations that we have found out just now, which is 4 meter per second. So I'd like to write down that 4 meter per second square. Just let me check one more time in case I remember this number wrongly. Let me see. Yeah, so it's 4 meter per second square. Therefore, from here we put down 4, and then we are interested to find out how far it moved. So I label that as x. From here we have x is equal to 1.6 by 1.6 here. So x is equal to what do you have here? 0.32 meter. Okay, so I hope that is clear. You can check with your calculator on this. I'm going to just double check in case I did it wrongly, but it shouldn't be any problem in this case. So let me see, 0.3, 0.3 is 32, 1, 2, should be, yep, correct. So it's 0.32 meters. It has already moved up by 0.32 meter just before the string breaks. Okay, so I hope that's clear. Now, what we are interested to find out is the duration of time from the moment when the string start to break at the speed of 1.6 meter until it reaches the ground again. All right. Now, of course, there are many ways to do it, but the most effective way is also using Soviet equation. So we are going to use the Soviet equations of S equal to ut plus half at square. But once the string has broken, for instance, that object will fall under gravity. So the only accelerations that the object is experiencing is just gravitational acceleration, which is g as 10 meter per second square. And then the displacement, I'm actually using this as a starting point, is final displacement with respect to where the string snap. Here we will label as s equal to 0 here. But the moment it reach the ground, right, the displacement is negative of this. So therefore, displacement is, we will take the initial is 1.6. The time is the one that we're interested to find. We know the gravitational acceleration is negative. Oops, I should put down negative 10 here, and then t square. And then the displacement is actually here. The final displacement is here, which is given by 0.32, and then that is actually given by negative 0.32 plus 0.52 here. And then that will give us like 1.6t minus 5t square equal to negative 0.84. And then by rearranging this so that we can form a quadratic equation here, we will have something like 1.6t and then minus 0.84 equal to a 0 here. Right? So from here, we're going to find out how long does it take. Okay, so just let me give it a try first. This one is pretty challenging, at least for me to factorize that. So you guys have a calculator, so shouldn't be any problem. So just let me key into my calculator also. 0.84 here. Okay, so we're going to have, let me see, what do we have here? We have here. Okay, so from here we sort of get a quite a nice number. We will get t equal to negative 0.28 or t equal to 0.6. Now, of course, because time is positive, therefore we will take the time as 0.6. Therefore, the time taken from the instant, time taken from the instant the string breaks until it reaches the ground or the floor again is given as 0.6 second. All right, so I'm going to pause here. I hope that is clear. You can check and cross-check your own methods there. All right, so I'm going to move on to the next one shortly. All right, welcome back. Let's look at this question here. ABC is a line of greatest slope of a plane inclined at an angle alpha to the horizontal, where sine alpha is given as 0.28 and then cos alpha is given by 0.96 here. Point A is at the top of the slope, and then point C is at the bottom of the slope. We are given that the length AC is 5 meter. So the part of the plane above the label B, you can see B is somewhere here. Above the label B is smooth. And then the part below B is rough. So particle P is released from rest A and reaches C with a speed of 2 meters per second. The coefficients of frictions between P and the part of the plane below B is 0.5. So here I'm going to write down the coefficients of friction is here. All right. Now, the first part, we are going to find out the acceleration of P while moving from A to B. So from A to B, because it's a smooth surface, therefore the only force that is acting on the object is the gravity itself. And then we need the component of the gravity, the weight along the slope. All right. Now, by using the first part, A by using Newton's second law again is equal to ma. We are interested to find its acceleration, which is a. The resultant force that is acting on the particle at this point is along the slope is mg. Here I write down along the slope is mg sine alpha. There's no other force acting along the slope. I'm not talking about the force that is perpendicular to the slope here. That will be ma. Therefore, by simplifying, we found that the accelerations of the particle between the surface AB is given as such g sine alpha. And then using g as 10 meter per second square, we will have the 10 by the sine alpha 0.28. Therefore, we get 2.8 meter per second square. Right? So that's the first part. I hope that's clear. All right, let's look at section B here. We want to find out the accelerations of the particle from B to C. Here, I'm going to redraw again the forces that is acting on the particle here. The same thing, we still have the weight component. We still have the reaction force. But for this surface between B and C, there is a friction. Because it's rolling down, therefore the friction is acting upward. Frictional force, I'm going to label that as Fr. Bear in mind, frictional force for B, frictional force is given by mu r. It's given by mu r. In our case, the coefficient of friction is 0.5. So 0.5 r. But how do I find out r then? So the same way we are going to resolve the forces perpendicular to the slope. So by resolving the forces perpendicular to the slope, we found that r is equal to mg cosine alpha, mg cosine alpha. And then from there, we can substitute it into here. We will get 0.5 mg. Do we have the m? Do you have the g? Let me see here. Do we have the mass given? No, we are not given any mass at all. So we will just write down as mg cosine. So 0.96 here cosine, and then let me just simplify that. So this one will be 0.48 then mg after we simplified. So that is the frictional force acting. By using Newton's second law one more time on B, we have F net equal to ma again. The resultant force acting along the slope is the same. The only thing different now is mg sine alpha subtract off with the frictional force, which is 0.48 mg is equal to ma, its acceleration. And then by rearranging, we found that the acceleration is given as g sine. G sine is 0.28 minus of 0.48 g here. So let me check one more time. Yeah, there you have it. Of course, in this case, we will get what we have here. We have deceleration. So we found that we have negative 0.2, so negative 2 meter per second square. Therefore, its acceleration is negative 2 meter per second square. Right, now I'm going to pause here for a while. You guys can check. I'm going to check also before I finalize this. Let me just check that very quickly. 0.2 mg right here. Then that is 0.48. Yep, correct. So therefore there is negative. Oh, sorry. It's a negative 0.2. I think I wrote it down wrongly. Hold on, let me change that. It's negative 0.2, not 2 meter per second square. Negative 0.2 meter per second. Hold on. Sometimes I make a silly mistake here. So let me see. That is 0.2. Oh, by 10. Yep, correct. I was right initially. So therefore, the acceleration is negative 2 meter per second squared. Right? So I'm going to pause here. I'm going to move to the next question shortly. All right, next let's look at how to find out the distance AB. Now to find distance AB, I'm going to label let distance AB equal to x then, right? So it's easier. And then first of all, before we do anything, we have to find out the speed at B. So to find the speed at B here, I'll label it as V in this case. By using the Suvet equations again, that will be V square equal to, because initial velocity was it was released from rest. Let me see. Yes, correct. It was released from rest, so therefore initial velocity must be equal to 0. So 0 square. And then the first section AB, it experienced an acceleration of 2.8. So therefore there will be 2.8 multiplied by the distance x here. And then we have a v square equal to 5.6x. Right, so I hope that's clear. That's the first part. We don't need to do anything here. And then the second part, BC. We know the distance. Since AB is x, then therefore BC, distance BC, must be 5 meter subtract off with x, because the entire length of AC is 5. Subtract off with the length of AB, you get the length of BC there. Now, by using the same Suvet equations, here I'm using W to denote the speed at the bottom of the slope. So here we will have W square equal to V square plus 2a. The accelerations now become the deceleration. The distance is 5 minus x, which is the distance of BC in our case. And then we know W is equal to 2. The V is given here, so we're going to substitute everything inside. 5.6x, because V squared is 5.6x. Here you will get, if you expand that, you will get negative 20 here, and then plus a 4x. And then eventually we get a 9.6x minus 20, and therefore 9.6x equal to 24. So plus that is equal to 24, and then 24 divided by 9.6. And then therefore alright, so the distance AB is 2.5. Therefore, we conclude that distance AB is equal to 2.5 meters. Alright, so I hope that is clear. I'm going to pause here. We're going to look at the third one shortly. Alright, let's look at our last questions for mechanics today. Right, we have a particle P is held at rest at a fixed point O, as shown in this diagram that I have drawn, and then release. P falls freely under gravity until it reaches point A here, which is 1.25 meter below O. Find the speed of P at A and the time taken for P to reach A. So let's start with number 1 first. So speed, we can use the typical Suvet equations for this. Bear in mind, Suvet equations can only be applied if the object is moving with a uniform acceleration. Okay, so we can use V equal to U plus AT. Okay, you can use V equal to U plus AT, provided we have the time itself. In this case, we don't seem to have the time. Therefore, we rather choose V square equal to U square plus 2AS here. Right, now we have the U, which is 0 square. And then acceleration is 10, displacement is 1.25 here. So from here, we can find quite easily. This is basically, let me see, 2.5, 25 here. That will lead us to the speed at P. The speed at A is 5 meter per second. All right. And then the time taken, yes, we can make use of the first equations one more time now by using v equal to 5, which is the same as u plus at. And then by solving that, we found that it take about 0.5 seconds to drop 1.25 meters free fall. Okay, now that is our first section. I hope that is clear. You can cross-check your own answer on this. All right, now I'm going to pause here. We're going to move on to the last sections for this question. All right, for question number 2, the object after pass A, it experiences an acceleration given as 10 minus 0.3 t. So from this point onward, we no longer can rely on Suvet equation because acceleration is non-uniform. Because the acceleration is non-uniform, therefore you have to apply calculus method, differentiation and integration. Now we know that acceleration is given by rate of change in velocity is given by 10 minus 0.3 t. Okay, right. Now in order to obtain the distance, we have to obtain the velocity first. Velocity is 10 minus 0.3 t dt, and then that will give us 10t minus 0.15 t square plus a c, right? Plus a c at t equal to, we are starting to measure because the t was measured right after a. So from here, we use a different measurement. So at t equal to 0, after passing through point A, the speed at this point is given as 5, which we have found out over here previously. That's equal to 5 meter per second. Now, by substituting this value into our velocity equation, we will get a definite answer for this velocity as, hold on, let me clear this, as 10 t minus 0.15 t square plus a 5. Because once you substitute t equals 0, the c is actually equal to 5. Now that will be our velocity. And then we're going to rely on this velocity to obtain the displacement. Because we know that velocity is the rate of change in displacement. Okay, we're going to differentiate that to obtain the distance. That is 5t squared minus 0.05 t cubed. Okay, t cubed, and then plus 5t plus a d, for instance. At t equal to 0, we start to measure the displacement from here. Therefore, our displacement should be equal to 0 when t is equal to 0. Now, because of that, we can conclude that our displacement function is given as, all right, so there you have it. Now, finally, we just need to find out the total distance p has fallen 3 seconds after it was released. Okay, now we know that it take about 0.5 second. Is it 0.5 second? Yes, 0.5 second to travel from O to A here. So the time taken is 0.5 second. Therefore, we will still have another 2.5 second. So within that 2.5 second, where would the particle be? Right? The total distance p has traveled. P has already traveled 1.25. Now we want to see another 2.5 second, how far it has traveled. So from here we have 2.5 square minus 0.05 2.5 cube plus 2.5 there. Right. Okay, just let me try out. Okay. You guys can also give it a try in this case. Okay, let me check on my calculator. That is 6.25 by 5. Okay. and then after that we need to subtract off with this 3 by 0.05. Okay, finally we need to add up with 5 by 2.5. Okay, that will give us 42.97 meters. And then therefore, we can conclude that total distance fallen from ore is equal to 42.97 plus 1.25, and then that will yield 43, oh sorry, not 43, it's 44. It is approximately 44.2. I leave it as three significant figures here. All right, so I hope that is clear, and then hopefully Janice will have a chance to look through this one more time. Hopefully this is clear to Janice, and then the rest will go through these questions here, right? So I hope it is helpful to your study, right? Until I see you again, all right? So stay healthy, and then keep on learning more mathematics and mechanics, right? Okay, until I see you again. Take care, everyone.